Now let us go over the position analysis of inverted crank slider. In this case, here the slider block has pure rotation with respect to a center O4, which is already at an offset from the sliding axis. So think of a slider block. This is like a cut section. There is this portion through which a second link can go through, and this block can rotate about a pivot. So that is the difference between the previous case and this case, where the slider block was not rotating with respect to a point. It was just translating along this axis of sliding. So if you note, because this is an integral part of this link, the link 4, so that you can define a geometric relationship between the sliding axis and the angle of the link 4. This is theta 4 for us, and this is the axis, and the axis can be defined with respect to this theta 4. There's an additional angle gamma. That's gamma here. So there's a fixed angle within the link 4, which defines the slot angle with respect to the link. We know we can always take from O to a vector RB for this point, which can be defined as R2 minus R3. But link 3 is now changing in length. This is between point A and point B. So the value of B keeps changing as the mechanism is moving. So B is one unknown, theta 3 is another unknown, theta 4 is the third unknown. So we have in total 3 unknowns, but with loop closure, we have 2 equations. Real and imaginary parts of the loop closure equation will give us 2 equations. So we need a third one, and the third one comes by relating the theta 3 and 4 through gamma. In the open configuration, as can be seen in this picture here, the theta 3 is equal to theta 4 plus gamma. For the crossed configuration, we have to draw something like this in the kinematic diagram, and we can note this is the angle theta 4 that's marked here in green. And then there is angle theta 3, which is marked here in purple. There's this orange angle, which is relating theta 4 and theta 3. That happens to be pi minus gamma, because this is gamma as defined based on an expression similar to this equation. All right, so that's the 3 equations and 3 unknowns. So we can go back to the real and imaginary parts of the vector loop and define or write down these 2 equations. From here, we can use the second equation to get B in terms of theta 2, theta 3, theta 4, and A and C. This can then be substituted here to obtain this big expression or big equation. We can rewrite this in terms of sine theta 4 and cos theta 4 only, with P, Q, and R being expressed in terms of known values of theta 2 and theta 4. So again, here the mechanism is a crank slider. And so there's input on the crank side. We know theta 2, and at any given theta 2, we're trying to find the position of the remaining joints, or we can say we want to find the values of B, theta 2, theta 3, and theta 4. We'll get to P, Q, and R shortly, but once we get this form, we can go back to what we did in the previous case. We can write the sine theta 4 and cos theta 4 in terms of the half angle formulae using tan theta 4 by 2, and then we can basically multiply this equation here with 1 plus tan square theta 4 by 2. That will cancel out the denominators and add an r times 1 plus tan square theta 4 by 2. Rearrange that, you get r minus q, essentially a quadratic equation in tan theta 4 by 2. Then you solve that, you get theta 4. From theta 4, you can compute B using equation 2, which is right here. And then you can find coupler angle using any of the using the appropriate relationship between theta 3, theta 4, and gamma. So quickly, to derive the expressions for P, Q, and R, this equation, multiply that by sine theta 3 on both sides, I get a cos theta 2 sine theta 3 minus a sine theta 2 cos theta 3 plus c sine theta 4 cos theta 3 minus c cos theta 4 sine theta 3 minus d sine theta 3 equals 0. Okay, this is a sine theta 3 minus theta 2. This is c sine theta 4 minus theta 3, and we can now use theta 3 equals theta 4 plus gamma. So this becomes minus c sine gamma. This becomes a sine theta 4 plus gamma minus theta 2, and this becomes minus d sine theta 4 plus gamma. And so now we can expand this and say it is a sine theta 4 cos gamma minus theta 2 plus a cos theta 4 sine gamma minus theta 2 plus we have this coming out to be d sine theta 4 cos gamma. There's a minus sign here, so it should be a minus. And then there is d cos theta 4 sine gamma. And then there's this term here, which is just minus c sine gamma. All of this is equal to 0. Now note, the only term which has no sine theta 4 or cos theta 4 is this, and that is r. If you take sine theta 4 common, you get a cos gamma cos theta 2 plus sine gamma sine theta 2 and minus d cos gamma as the term. So this should be p. You can note by taking now cos gamma common, you get a cos theta 2 minus d cos gamma plus sine theta 2 sine gamma multiplied by a here. That's p. So we got that right. And then we can do the same. Take cos theta 4 common. We get a sine gamma cos theta 2 minus a cos gamma sine theta 2 minus d sine gamma. This should be q. We can take again sine gamma common and write this as a cos theta 2 minus d sine gamma minus a cos gamma sine theta 2, which is exactly this.